In this session, let us explore about trees, a brief introduction to it. A tree is a collection of nodes. It can be empty, otherwise, it will consist of a node called a root and 0 or more non-empty subtrees in it. Like this. This is the root, and T1, T2, T3, etc. are the subtrees in it. This is one more example for a tree. In a tree, a root is one which will not have any parent. So here, the root is A. It's not having a parent. A node is defined as the item of information. Node F has A as a parent, and the children of node F are K, L, and M. Leaves are the nodes with no children. In this tree, these are all the nodes which are called as leaves because they don't have any children. And siblings are the nodes with the same parent. Here P and Q are the siblings because they have the same parent J, and K, L, and M are the siblings and they have the same parent F. A path from a particular node N1 to Nk is defined as the sequence of nodes N1, N2 till Nk. For example, path from A to L will be defined like this: A to C, C to F, and F to L. So this is the path for reaching L from A. And length of the path will be the number of edges on the path. The same tree, let us consider path A to L will have a length 3. A to C1, then C to F2, then F to L3. So totally 3 edges are there. A degree is the number of subtrees of a node. For example, degree of A is 4. We have 4 subtrees in it, like this. And degree of D is 1. It's having only 1 subtree. Degree of E is 2. It has 2 subtrees in it. The level of a node is defined by initially letting the root to be at level 1. So if a node is at level L, then its children are at level L plus 1. In this case, the root node A is at level 1. The child E of the root node A will be at level 2. So the level of J would be 2 plus 1, that is 3. The depth of a node Ni is the length of the unique path from the root to Ni. The depth of node L is 3. A to C, C to F, F to L. So the unique path from the root to Ni from A to L would be 3. The height of a node is the length of the longest path from that node to a leaf. For example, height of node F is 1. And then all the leaves will be at height 0. The height of a particular node is the length of the longest path. So height of a node F would be 1. A binary tree is a tree in which no node can have more than 2 children. When we are comparing a binary tree with a general tree, a binary tree will have maximum of 2 children, whereas a general tree has any number of. A complete binary tree of height h will have the number of nodes between 2 to the power h and 2 to the power h plus 1 minus 1. And all the elements should be filled from left to right, like this. Representation of a binary tree. There are 2 ways for representing. One is a linear representation, the other is a linked representation. In a linear representation, as you could see here, we start with the root node A, and then the next level B and C, and then comes D, E, F, and G. This is how all the nodes in a tree would be represented using this technique. In a linked representation, the elements are represented using pointers. Each node will have 3 fields. One, a pointer to the left subtree, a data field, then a pointer to the right subtree. In a leaf node, both the pointer fields would be assigned as null. In this example, the root node A will have a pointer to the left subtree, a pointer to the right subtree, and the data node. So whereas all the leaf nodes D, E, F, and G will have a null value to the left and the right pointers. So whereas all the other nodes A, B, and C will have a pointer to the left subtree, a pointer to the right subtree, and the data field. An expression tree. The leaves of an expression tree are operands, such as constants, variables, and the other nodes will contain operators, like this. So here, this is the expression tree for this expression, wherein all the operands are represented as the leaf nodes and all the other operators are specified in the remaining nodes here. When we compare a binary tree with a binary search tree, a binary tree is one which can have at most two children and it doesn't have any order. This is one example for a binary tree. Whereas a binary search tree is one in which the key values in the left node would be less than the root and the key values in the right node would be greater than the root. So they are maintaining some order in some consistent manner. This is one example for a binary search tree. This is at the root and all the nodes to the left of the root node will be less in value, whereas all the nodes to the right of the root would be greater than the root. Every binary search tree is a binary tree. All binary trees need not be a binary search tree. Let us consider an example. We are going to insert these elements in the specified order. The first element, let us consider it as a root. And when we try to insert 5, we compare it with the root and we find value 5 is less than the root. So it has to occupy the left. The next element is 10. When comparing this 10 with the root, we find 10 to be greater than 8. So it is towards the right. Similarly, the rest of the elements are traversed. Now 15, we find it is greater than 8. So we move towards the right. It's still greater than 10. So we move towards the right of 10. It occupies this position. Now after 20, the tree looks like this. That is, you compare 20 with the root. You find it is greater than the root. So it goes to the right. And still 20 is greater than 10. So still it goes to the right. And it is greater than 15. So it goes to the right and occupy this position. So whereas after 18, the tree becomes like this. You compare with the root, it's greater than 8. It goes to the right. You compare it with 10. So it's greater than 10. It goes to the right. It's still greater than 15. So it goes to the right. But when you are comparing 18 with 20, you find 18 is less than 20. So instead of right, it's going towards the left and 18 occupies this position. Tree traversals. Traversing means visiting each node only once. We have three traversal techniques: in order, pre-order, and post-order. In order traversal, the order of performing is left subtree, root, and then the right. So the resultant expression you get is the infix expression when we perform in order traversal. For example, this is the tree we have. The in order traversal would be left subtree, then root, then right. So it would be 10, 20, and 30. Then pre-order traversal, it is performed in this sequence: root, then you traverse the left subtree in pre-order, then right subtree in pre-order. So this pre-order traversal will result in a prefix expression. For example, in this tree, when we perform pre-order traversal, it would be root, left, and then right. So it will be 20, 10, and 30. Post-order traversal, the order is like this: left subtree in post-order, then right subtree, and then root. This post-order traversal will give you the postfix expression. The post-order traversal, once performed in this tree, would result in first left, right, and then the root. So it will be 10, 30, 20. Thank you.